Dear students, good afternoon. So today we'll be discussing a very interesting topic about coherence, the concept of coherence and laser. So these two, actually, if you have to study laser, you have to have a very good idea about what coherence is. Okay, so the term coherence refers actually to the degree of correlation between the phases of different points in a beam of light or radiation. It could be, coherence can be in any radiation. It might not be only of visible, it is not restricted to only visible light. So it is the degree of correlation between the phases. Of correlation between the phases. Okay. At different points of radiation. In a beam of light or radiation. So this actually plays a very vital role over here. Now coherence, it is of two types. You have temporal coherence and you have spatial coherence. Okay, so do you have any idea of what we mean by temporal coherence? Temporal coherence is actually, when we discuss of temporal coherence, let us talk about, let us consider a one-dimensional plane wave. A one-dimensional plane wave. Okay, if we consider a one-dimensional plane wave, how will we represent that wave? Let us consider the representation of that wave as psi xt, and let it be equal to a e to the power I kx minus omega t. This is the representation of a one-dimensional plane wave. I hope all of you will agree to me by now. Well, so actually I could have written this as y equal to a e to the power I kx minus omega t. Okay, so whether I write it as y or I write it as psi, it will actually represent displacement at any time. So this actually is your displacement at any time t, isn't it? So I repeat, it could be y, x, it could be anything. I am putting it as psi as a function of x and t. It is displacement at any time t. What is a? All of you know that a is the amplitude of the wave, which is actually a complex quantity. So a I can write as, well, mod of a e to the power I phi. It is a complex quantity, this amplitude, such that your representation for the displacement psi xt, it is actually a, alright, e to the power I kx minus omega t plus phi. This, if you break up as a cosine function, what do you get? This is equal to mod a cos of kx minus omega t plus phi plus I sine of kx minus omega t plus phi. Okay, so this is it. All right. So, well, if you consider the actual displacement, the real part, then it is a cos of kx minus omega t by psi plus psi. This is your actual displacement. Okay, so you see over here, then if you look into this equation, you can always say that there is a kind of a correlation in of the propagation of the wave with respect to time. What kind of correlation is it? What can we say about this correlation? According to this equation, you will say that the displacement remains sinusoidal for all times. Okay, but in actual practice, there is no source which is a point source. Okay, and there is no source which you can always claim to be monochromatic. So what you can say is that a pulse is emitted. Okay, when is a pulse emitted? When an electron jumps, say, from one orbit to another orbit, from a higher lying level to a lower lying level or the ground state, and then it releases the energy difference between the two levels. So the light wave that is released is of a very short duration. The duration of the release of the light wave is of the order of 10 to the power minus 10 seconds. This is the duration of the pulse. Duration of the pulse that we get when an electron jumps, say, from one level to the other level. So this field remains sinusoidal only for this small instant of time. Okay, this time is the average lifetime of a wave train. When a wave train is moving, we cannot say that throughout its motion for all times. Okay, well, the wave train will have the same phases. Okay, it is this time within which a pulse is emitted. Okay, and this time is known as the average lifetime. So average lifetime of a wavelength is very short. It is of the order of 10 to the power minus 10 seconds. Okay, so the emission of light from different atoms or even from the same atom at different times is a very random and arbitrary process. Okay, therefore the phase of the light sources that we get from the natural sources are very random. They are not correlated. They are not or never in phase. Okay, so then we cannot say that these wave trains are in coherence. All right, so they does not possess temporal coherence. What then is temporal coherence? When a beam of light is said to have phase difference same, suppose say if two wave trains are crossing a point, if you have a wave train like this, and suppose say it is moving in this manner, the wave train. Okay, so if two of the points over here that you have, if they are crossing the 2 points lying along the same direction and are having the same phases independent of time, then we will say that these 2 points have temporal coherence. I repeat, a beam of light is said to possess temporal coherence if the phase difference of the waves crossing 2 points, say point A and point B, lying along this direction of propagation of the beam is time independent. Okay, so it is also known as longitudinal coherence. So if the phases are time independent, we say temporal coherence is said to exist. Okay, So the time interval over which the phase difference remains constant, we call this the coherence time. So this time interval tau c, if I call this as tau c, then tau c is the coherence time. Okay, this concept is very important for the understanding of laser. So please let me know if you've understood it. Okay, let's stop.